Ladies and gentlemen, my name is Flavio. I am the CEO of Relab, and I am one of the founders and CTO of Recupera. And I have been asked to explain to you about our gasification process, why it is different of other processes that are out there. What is the innovation height of our process? Why I think it is so innovative. I will try to do that. As you may know, I am a retired professor of chemistry, and here I put my attire in respect to you that are searching for knowledge. I was trained in Germany, and in German we are advised to wear the formal dress when we are meeting our students. And the reason is respect for the students. So in respect of you, I put here my uh, professor attire and come to the speak of why what is the process. So if you bear with me, I will just start a short presentation and go through it with you. Just bear with me for a second. I have, of course, to find everything I hear. Okay. So there we are. And I have just to say that this process here is how to start the presentation. There was a way of starting the presentation. Okay, that is, you don't need. Let me start by saying that both Recupera and Relab and Resynthesis technology is exactly the same. So the technology was in fact developed by our team at Recupera in Slovenia, but it has a long story behind it. But in the end, it was constructed and validated in Slovenia. So we have constructed our reactor in the commercial scale. We have only one scale to make it very clear. There is only one scale of equipment, and that is the prototype scale that we have used in Slovenia to validate the technology, but it's also the commercial scale. It's not different, which make it simple because it's only one scale. And the reasons for this one scale, I will try to speak later in the thermodynamics. So the objective of this presentation is to unveil the rationale of Recupera and Relab waste plastics gasification process. The data comes from calculation, from simulation, and experience that we acquired under many years of development. It took us decades to come to the point that we are today. Let's make a resume here about our what we call low temperature conversion gasification. And let's also say this is one of the important point. What is different from everything else? Low temperature. Low temperature gasification is something we have pioneered from an idea set forth in German, in Tübingen, but it was never reduced to the practice in German. So we were the company that started, developed the gasifications to work with this technology. And this technology has one thing that you should remember, is gasification below 450 degrees. Why that is important, I will come to that later, but this is very important. The state of the art of gasification, there are two technologies available out there. There are, in fact, some 100 different types of gasifier. They are all different, and everyone was created for a specific purpose. So the purpose of the gasification is very important, the design and construction of the gasification. You have always to ask, what is the purpose of this gasifier? No? But the gasifiers out there, they either work around 2000 degrees centigrades, or if they are plasma gasifier, they will be around 4500 degrees. So very high temperature. We, on the other way, work below 450, and I will try to explain that. The process capacity of our gasifier, both the prototype and the commercial scale, is the same, 1 ton per hour of process capacity. Our feedstock must be treated in a special way, almost pulverized. This is important for the technology of gasification, but that is a difference. I would say the innovations that we are bringing in, besides the temperature, is also the gasifier itself. And this is a process. All the technology that we have developed to create this gasifier with the purpose, and I will explain the purpose of our gasification. Gasification, of course, does not accept the moisture. So the moisture must be below 20%. Gasification temperature, I spoke. The pressure, this is very important. It is normal pressure. So some people will start always saying by me, I know it's high temperature and high pressure. No, it's not. It's not high temperature. It's not high pressure. It's normal pressure and low temperature. That is how we do it. Some others, how others do it, well, I don't know. And of course, it is a steam reform. So we use steam to oxidize, to provide the oxidant for this gasification. I will speak about gasification. And one important point, water shift is not part of gasification. A lot of people say, oh, you have to gasify and do water shift. No, you don't. You don't have people who says that they have no prima facie experience in gasification, because even the equipment is separate. Normally, I agree. Normally, when you gasify hydrocarbons, you do both reactions. But this is normally. We are not speaking about normally. We will speak about what we do, and the reason will come. So normal pressure, no water gas shift. It is a Gemini gasifier with two 10 meters serial towers with two cyclones and 18 independently addressable segments, which can be considered as gasifiers. So we would say I have 18 gasifiers in series. And why we do that, I will explain later. But these are the technology that provide the quality of our gas. And what differentiates us from the rest? The quality of our gas, the way we do, and the quality of our gas, because this is fundamental to the purpose, to the applications that come down. And of course, the application is downstream processing. So we produce, we develop a gasifier that produces a gas that is not to be burned. The gas is not to be considered a fuel. The gas is not to be used to process, to produce energy. The gas is to be used to chemistry as feedstock for renewable chemistry. This is the reason why we develop our gasifier. One important point, gasification occurs almost quantitatively. If people who knows gasification, they will know that. So gasification is different from pyrolysis, where you have three phases. But I will speak about that. It's almost quantitative. You will get 99.9, 99.99, and if you purify 99.999% syngas. And syngas, this is definition is very clear and is in the literature since 200 years. So please, this is not really new. This is something that's very, very well established. Syngas is a gas composed essentially of hydrogen and carbon monoxide. Of course, in this 200-year history, the quality was not always the same. So syngas in the beginning was very dirty, very contaminated with a lot of stuff. But with time, more and more syngas has been cleaned and produced with high quality, and high quality syngas is only hydrogen and carbon monoxide with a relation 2:1. So this is by definition syngas. Now, let me tell why we choose gasification. We could have gone to other technology, and of course, in recycling of plastics, there are many technologies out of that. Why we choose gasification? Because gasification, if you compare, there are technologies which are biological and they are thermodynamical process, recycling process. I'm talking the feedstock waste plastics, but could be any carbonaceous feedstock here. Could be wood, could be biomass, you name it, as long as they have carbon. Gasification is the straightest way to producing hydrogen and carbon monoxide. And in many applications, you are looking for hydrogen and carbon monoxide pure. So there is no other way to produce as straightforward as gasification. And that is the reason we have gone for gasification. Of course, after the gasification, if you want to boost the production of hydrogen, you may go to a water shift reactions. You may add a separate reaction, but this is already downstream processing. Gasification, one step gasification, and you have syngas. And this syngas, as I'm stating here, can be used for synthesis. And I will speak about that later. But this syngas can be used, so gasification is the straightforward pathway for producing gas. All the other technologies will give a lot of steps to come to the same thing. And each step, if you understand thermodynamics, you know that each step you have to pay something. There is no free lunch, not in thermodynamics. So that is how. Now, let me speak about the most related technology, because all the time people get somehow confused about that. And there are three technologies. They are related. And these technologies are pyrolysis, gasification, and incineration. They are related, but by no means they are something. They are exactly, they are not. They are completely different. Pyrolysis is a technology that is anoxic. There should be in a pyrolysis reaction no oxidant whatsoever, because you are breaking the molecules internally with heat only. It is allothermal. It means that you need to add external source heat all the time. You need to add heat to the systems all the time. And pyrolysis produce always three products: char, oil, and a gas, which we call strong gas. By no way this gas is to be called syngas. It's not syngas. This gas is the gas from the homologous series, C1 to C4, and this has nothing to do with syngas. Cannot be syngas because you don't have oxidant. If you don't have oxidant, you cannot do partial oxidation. Gasification, which can run, pyrolysis can be run from 450 to 2000 degrees. That's normally the temperature people run pyrolysis. Gasification is an autothermal. It is slightly exothermal. It's slightly exothermal technology, and this is a partial oxidation. Partial oxidation means not completely oxidation. Complete oxidation is incineration, burning, mass burning. That is completely incineration. Pyrolysis, you use sub-stoichiometric, if you understand the chemical expression, sub-stoichiometric quantities of the oxidant. And the oxidant can be oxygen, can be air, and can be steam. We use steam. And what is the product of gasification? There is only one product, and this is 99%, 99.999, if you want, syngas. And syngas is a gas composed solely of hydrogen and carbon monoxide. And the third technology is very common. This is incineration. You just burn. And everybody knows that plastics, biomass, they will burn. Then we burn with excess air, excess oxygen. What you get as a product, you get heat. The only product that you can use as a product for incineration is the heat. Incineration is the most exothermal of the technology, the one that produces the largest amount of heat. You produce a lot of heat, and because the material always leads to 1200 degrees. So incineration is always 1200 degrees, and to be completely incineration, you have only heat available. The other product of incineration is CO2, but you cannot do anything with CO2, and steam. So incineration produces CO2, steam, and steam was not really the product, but you produce a lot of heat. And this heat may be what you want. You want to produce heat for boiling water, for doing something. So you should consider incineration as well. And then you couple to a steam boiler and you can have power. This is the secondary refining step. So you produce the primary product. Here is heat, here is syngas, and here is the three fractions. You can use pyrolysis and then you can activate it, you can extract, you can reform and you can separate and come to chemicals and come to different technologies here, but by no means the most flexible one where you can have everything is to producing syngas. You produce a syngas, and of course, then you have the whole of the chemistry. Through synthesis, you have the whole of the chemistry. You can also separate, and you have hydrogen, you have ammonia. You can, by synthesis, convert to methanol, and from methanol, all the chemistry. So this is by far the most flexible and also the highest purity, because one of the big problem of using this technology here is that your product, which is the primary, which is this mixture here, this complex mixture, can be just too complex for separation. It's not easy to go from oil and then extract the oil and take out the chemistry. So please, I have a lot of experience working many years with pyrolysis. So don't you believe for a moment that that will be easy. It's not. It can be very complex, and I have seen many projects based on pyrolysis. They fail because they could not do the extraction and the separations out of the pyrolysis oil. So, and I'm thinking about chemical companies. I will not name them now, but very renewed chemical companies have failed. So it's not easy. It's not easy. Syngas has been around for 200 years, and people have been producing syngas for many different applications. And as I said, not always the syngas has been clean. It depends, because if you are producing syngas as street gas for incineration, you don't need any cleaning. You go directly to burning, because that's a fuel. Syngas will be a fuel directly. You don't need to go to over any scenes. This is a direct way as a fuel gas. So as a fuel gas, you don't need much. Only the law may require you to do some purifications today, but for 200 years ago, there was no law requiring you to do anything, and people did not clean anything. And so it's easy to get there. Now, I just want to make it now a kind of a resume of what I have been talking, thermal treating benchmark. So combustion, the main product is heat and flue gas. And the flue gas is not fuel gas. The flue gas is the extinct carbon dioxide, which have energy as long as it's hot. Because when it's cooled down, there is no energy. You cannot use for anything. So heat and flue gas. Gasification, a combustible gas, and this combustible gas is syngas and heat. That is gasification. Pyrolysis, you produce an oil, which is combusted. You produce a complex gas, not to be confused with syngas, and you produce char. The energy balance, combustion is extreme exothermal. Incineration is the most exothermal. Gasification is autothermal. It means all the heat you need in the process will come from the material which you are gasifying, especially when your material is plastics. When you are gasifying plastics, all the energy you need will come from the plastics. You don't have to add any energy to the systems. And pyrolysis is a completely allothermal process. You will always have to add energy to the process. The main product constituent, of course, combustion is CO2, water, and nitrogen. Nitrogen is not a producer, but comes from the air, no, of course. But you have CO2 and water, as I said. Gasification, you will have syngas, and syngas is carbon monoxide and hydrogen. And that's it. This is syngas by definition. There's nothing else. The other things that may have here is contamination, and you don't want to have contaminations in a pure product. And the third technology is pyrolysis, oil, tar. because a lot of people are asking me about what's the tar here. Tar is not here. Tar is here. Here is the tar. CO2. You can have some carbon monoxide, but not much. Hydrogen, minimal amounts of hydrogen. Methane, you will have methane, CO2, and water and char. No. Oxygen is stoichiometry. This is the oxidation, the lambda factor. For combustion, it's just 1 to 1, typical 1.23, because you need excess oxygen to drive the combustion. What is the relation, the lambda relation? It is between 0, of course, and less than 1. So if you go to 1, your gasification will be combustion. You don't want to have that. Remember, these processes are related. If you have 0, you will have pyrolysis. You don't have gasification, you have pyrolysis with all the problems of pyrolysis. If you have too much, close to 1, you will have combustion in your gasification reactor. So to have reactor, typically is here, 0.2. The relation is 0.2 to 0.4. You have to sort out because it depends of the composition of the material. If the material like wood has already oxygen, so you don't need so much oxygen because you already have oxygen in the material. But plastics normally have no oxygen. So you have to add that. An oxygen can come from the air, can be pure oxygen, and can be oxygen from steam. Steam has also oxygen. So that's it. But the relation is very important. Chemical, this is very important, the chemical reactivity of the main product, the primary product. When you do combustion, the primary product is inert. You cannot do any chemistry with it. It's dead. It goes nowhere. Gasification produces a gas with a very nice heating value. It will be here around 5. It is, if you are work with plastics, it will be more like 11 to 20 megajoules. So quite a nice energy that you can use for doing a lot of things. Now, exergy is the name of the energy that can be used for doing work. That's exergy. So this is the difference, and I hope I have explained the difference between combustion, gasification, and pyrolysis before we can start now talking a little bit further. Now, a lot of people come to me to use the systems for producing hydrogen. And hydrogen is one of the two products of syngas. Syngas is carbon monoxide, which is a commodity, and the other commodity is hydrogen. Everybody's looking for hydrogen. There are different methods of producing hydrogen. And here is I stolen from Shell. And I just add plastics here because Shell had up to coal and oil and natural gas and solar, wind, algae, biomass. So they are different processes. But one that is commonly forgotten is that one here. Plastics are hydrocarbon, which means they are composed of hydrogen and carbon. And of course, we can consider plastics as carriers of hydrogen and carbon, and carriers of renewable hydrogen and carbon. And of course, there is the technology that we use, steam reforming. And of course, you take plastics, run in the term of in a steam reform, which is gasification, and you have syngas. And syngas can be separated to hydrogen. So this is totally correct. Shell is one of the largest producer of syngas in the world, so they know it by the core. Now, we have decided both in Recupera and for all in Relab to work with plastics. One of the reasons for that is plastic have more energy than oil. Plastics, mixed plastic has 39 megajoules per kilo. Fossil oil has around 44, 42. It depends of the quality, but 42. And here is, we have with 39, the mixed material. If you go to certain types of plastic, like this one, HDPE, this has more energy than fossil oil. This has more energy. So here we have a material with higher value of energy than fossil oil. Why should you be using fossil oil when you can use HDPE and LDPE and PP. These are the so-called olefinic plastics. So olefinic plastics are by far the best material you can use to gasify. And it's of course why we're looking for that. No, so here are different materials that we gasify. So often they ask me, what about PVC or PFTE, brominate, anti-flame? No, we are not looking for them. And the reason is that PVC, when you gasify, it produces the acid, which is hydrogen chloride. And hydrogen chloride is a very strong, and also fluoride is a very strong acid, and that will corrode the equipment. In order to have a long life of our equipment, we must reject that. The tolerance is 2%, but we are really not looking for those modified with halogenated. No, these are halogenated plastics. And the reason is because they destroy the gasifier. Of course, we could construct a gasifier that would tolerate this. We have been there. I have already tried that, and you can do it. It's only that's much more expensive to produce. And normally, plastics, the 80% of the plastics, packaged plastics, is here. So you don't really need to go to PVC. PVC is today not common for many reasons. Um, so these are the plastic we use. Now, I don't want to go there, but this is the chemical form. I just want to stress when I say that plastics are carrier of hydrogen, this is a typical plastics. This is a typical olefinic plastic. You have carbon, and each carbon carries two hydrogen. This is the chemical structure of plastics, and that is how it is. We cannot change that. And it's very important that you understand that. Since plastics are carrier of hydrogen, we have in waste plastics an excellent material source for green hydrogen, which we have started by calling, because we have to separate from green hydrogen, which is people mean the one that is produced by electrolysis. This is not electrolysis, this is chemical produced, so we call it white hydrogen. But hydrogen, as you know, has no color, so call it as you want. Hydrogen from carbonaceous waste material is the what we are talking about. Now, energy content of plastics, just again, there are different tables. People have computed different, but I'm talking about this one here. The average heating value is, as I said, 38 or 39, and the high heating value here is around 40. And this is low heating value and the high heating value. You can choose. Now, of course, in all, there are different numbers which are given in the literature, but Felix is the one that people most likely use. As long as you use one technology or source of information, you should be fine. Now, for gasification itself. Now, and this is a very important, because people are asking me how to do it. And of course, it's not so simple as you put plastics and the other side you have a syngas. There is a process here. There is a thermal process, and gasification. This is a typical gasification diagram that you have carbon, you have hydrogen, and you have oxygen. As you know, oxygen is the oxidant here, no? And here you have the carbon, what you want to oxidize, and here you have hydrogen that you want to produce. So if you start with very low, as I said, below almost zero oxygen content, you are doing pyrolysis. You are here at pyrolysis. You are not doing gasification at all. And the product of pyrolysis are those three phases: carbon here, you have producing carbon, and you are producing some oil, some carbon oil, and you have producing some gas, and the gas of pyrolysis, this would be the major one, methane. But you have methane, ethane, propane, and butane. They are all gas, and they will be mixed. Ethane, especially methane and ethane, will be mixed. This is ethane. Ethane and methane, they will be mixed in the pyrolysis gas. But of course, you are not producing any syngas. Only when you come to the relation between 0.2 to 0.4, no, that is where you start seeing syngas. Then you have syngas. When you are seeing syngas, then you have gasification. Because as I said, gasification, the syngas is the product of gasification. And only when you have gasification, you have syngas. If you have pyrolysis, there is no syngas. Because this here is not syngas. Syngas, now you know, is hydrogen and carbon monoxide. And syngas will be here. No, as you need to add steam to drive the syngas, but that is the area that you gasify the plastics here, no? And you are producing hydrogen and you are producing carbon monoxide. So this here is the area of carbon monoxide. When you start in your gasification process seeing CO2, you know you are having combustion. You are having combustion, you are adding too much. And in fact, you have to use the presence of CO2 to regulate. It is a sensor of your reaction is going too far to the oxidation. So you have to throttle the gasifier in order to maintain here. This is a fine dance. It's a dance between carbon, oxygen, and hydrogen. And how to control this dance can be complex. That is why we have invested a lot of time in developing the software. It is part of our innovation, the software that controls this dance of atoms that is responsible for gasification. One point I want to tell, especially when we are gasifying plastics, to consider. Plastics is composed of carbon and hydrogen. It may have other atoms, heteroatoms, especially in contaminations, but plastics are mostly derived from naphtha. And naphtha has been purified. Naphtha is not raw oil. Naphtha has been purified, and sulfur has been removed from naphtha. So plastics are purified hydrocarbons. And that is also the advantage. Why should you go for unpurified hydrocarbons, a source for your chemistry, when you can have already purified the material that people are now considering a waste? Plastics have normally no moisture. Plastic may have moisture if they stand in the nature and got humid and it's raining over it. But if not the case, there is no ashes. It's very important to notice. Plastics have no fixed carbon. So there is no fixed carbon different from biomass. That is the reason you don't get carbons. You don't get cars when you are gasifying plastics. Plastics gasify, as I said, to 99.9%. So the ashes will be any mineral. It depends of the temperature you are gasifying. In our case, since we are not volatilizing the inorganics, all the inorganics available in the plastics, all the metallic, inert contamination, they will be in the ashes. If the plastics are not heavily contaminated by silicates, by earth, no, which normally is not the case. If the plastics are not heavily contaminated, the amount of ashes would be minimal, 0.1%. This is what you should expect, 0.1%. Of course, if the plastics are coming from agriculture, fully loaded with earth, then of course you have a lot of ashes here coming from the earth. But if the plastics are coming from packaging plastics, they may be contaminated with some ketchup or mustard or whatever you have been messing around there, but it's not really much. And very important, plastics have no fixed carbon. This is biomass. Biomass has fixed carbon. So that is also the volatiles. Plastics are very volatile because carbon hydrogen goes directly to 99.9% to the gas phase. So you are not expecting anything. Low sulfur, very low sulfur. Plastics, for instance, polyamide has, of course, amine. So you have the amine ammonia coming from polyamide. But if the plastics are not polyamide, if the plastics are olefinic plastic, there is no nitrogen, there is no sulfur, there is only, and also no oxygen either. No, the plastic has only hydrogen and carbon, as I showed you the form. So this is the only thing you have to. Now, gasification has been around for a long time, for a long time, no, 200 years. The first gasifier was built in England 1823, so 201 years to be exact. And it's not magic. It's nothing to do with magic. Gasification is a chemical process and quite complex. These are all the reactions. Now, I'm not going through all those reactions to explain, but those reactions, many of them cancel. You see here, you are producing CO2, but down there you are using CO2 for the reaction. Here you are using the CO2, so they cancel itself. And the overall reaction for plastic is the one here. This is carbohydrate. The only thing you need to know. Carbohydrate will react with the steam, and steam is water vapor. No, steam has hydrogen and oxygen, and it will produce hydrogen and carbon monoxide. So this is the reactions, and this is totally based in science. There is 200 years of evidence to that. I'm not inventing anything here. It's so basic features of a plastic gasifier. One, it must be able to provide high heat transfer ratio. It has to. There are many gasifier design that do not allow for that. And if you don't allow for that, you'll not be able to do. That is the reason we have so many segments in our reactor, and each segment is addressed thermically, no, by radiation independently. That is to guarantee a high heat transfer all the way. And this is, of course, we are the only one. To the best of my knowledge, I know some Japanese have 3 segments, but they cannot compete with our 18 segments. So the king of segmentation, we are. Capable of handle the stick nature of molten plastics. Yes, plastics will melt, and this may cause agglomeration, cause some problems. But these are things that people working with the problem solve. We have solved. We have solved. So this is not at all a problem for us. But there are technologies that need to be implemented. And the third, you need to have the appropriate residence time. If your time is too short or is too long, you have problems. So the appropriate residence time you have to calculate and you have to determine, but it's milliseconds. So it's very, very, very fast. The reactions are very fast. And of course, in some cases, you want to be able, especially depends of the contaminants or how the type of the plastics, you may want to use different catalysts and for several reasons, even for purifying the gas. So you need to be able to add catalysts in your gasifier. But these are very simple features, very simple feature. We have done a lot of work to have this process done this way. Now, and then, of course, we can compete with many others type of process. Depends on what you want, the desirable syngas property. If you want syngas to be used as a fuel, as I said, purification is not really necessary. You don't need to purify. Also, the quality of the composition, the division of the gas to fuel is not important. Syngas will always burn. So you have a burn gas. You don't. If you want now to produce hydrogen, you may want to have a high rate of hydrogen to carbon monoxide, obviously. Now, and to get to this high age, to this highest rate, you may even add some process like the process of water shift reaction. You may add, but if you add water shift, you will produce CO2. And that is a decision you have to make. Do I want to produce CO2 or do I want not to have any emissions at all? If you don't want to have any emission at all, you just skip the water shift. And then you have a very high production of hydrogen and carbon monoxide, not carbon dioxide. And of course, contamination is very important. If you're doing chemistry, you need to reduce the contaminants because the contaminants will poison the downstream process. So if you are doing any chemistry or even producing hydrogen for some chemical applications, you need to get sulfur down. And to do that, you need to clean the gas or use materials that does not produce sulfur first place. You have to watch up the sulfur concentration. But of course, the heating value for a chemical gas is not important. The heating value is important to fuel gas. You are not increasing the heating value. You are not using for heating. You use as a chemistry. And of course, here the different pressures here, because this is not associated to us, but in our case, the pressure is close to one. At 1 atmosphere, 1 bar, that is the pressure. And the temperature already here is very low, 100 to 200 centigrade for hydrogen you want. But if you want to do the syngas, the optimal syngas, it has to be above 200 degrees, because 200 degrees is the ceiling temperature of plastics. You will not gasify plastics below 200 degrees. So it have to be above 200 degrees. But anything from 200 to 450, which is our maximum temperature, no? And why are these the maximum temperature we want to go? Because a benzene polyaromate is starting forming 500 degrees, 500 to 700. And a dioxin is a polyaromate. So dioxin will also form around this temperature. And we don't want to have dioxins. We don't want to have aromates in our gas. And we don't want to have any contamination with this very dangerous substance. And that's the reason we do the reactions below 450 degrees. The gasification itself, people, as I said, there is no mystery, it's not magic, but you need a gasifier. And of course, it is dependent of the parameters that we spoke about. And of course, you can count the molecules. The molecules that you feed in are the same that you found as a product and in the ashes. And if you will remove as a contaminant, because this is what can happen. Everything goes in and then become syngas, that's the product gas. And then you have some ashes, which, as I said, 0.1%, and you may have some contaminants which you are removing because you don't want to have them in the product gas. What determining the syngas in high quality? The mass flow rate of steam. So if you are, as we are, gasifying with steam, you need to have the flow rate of steam under check. The feedstock, of course, the feedstock is very important, and different feedstock will give different results. Very clear. The mass flow rate of oxygen. If you are gasifying with oxygen, you need to compensate the mass flow rate of the oxygen as well. The gasification temperature, absolutely important. And as I said, we work below 450 degrees. And of course, then you have to set all the parameters to be able to work under 450 degrees, as we do. And then you have, of course, homogeneity. How homogeneous are the material? This is preparation of the material. You have to prepare the material in a certain way that's very homogeneous. We said that we pulverize, and the way of increasing homogeneity is to pulverize the material. And of course, the residence time. We have for each reactor, each segment, a very specific residence time that we control very well with our software. And of course, by doing so, then you have here the plastics pre-treatment workflow. We get plastics with a mixed, dirty, we collect, the plastics are pressed, sent to a warehouse, and from this warehouse, we take the amount of plastics we need on a daily basis, we shred, we micronize, and then we give the plastics to the gasifier. So this is the basic pre-processing that we need to do. And then you have here the gasification process. The dry and pulverized plastics or carbon cells, they are gasified with steam, with oxygen, with heat, if heat is provided by the process, but when you start up, you need external heat. And then when the gasification process starts, you're using the gasification, the heat from the plastics, but you need the heat. And then, of course, you are producing some small percentage of ashes and producing your gas that may contain some contaminants if they were present here. If a mine was present, we will have NH3, ammoniac. You have ammoniac here. If sulfur was present, you will have a sulfhydric gas here, no? But if none of that was present, and also if you do the gasification well, you don't have CO2, you have only CO and H2, which you can or not, now pass through a purification. And then you have a pure syngas here. And then, of course, methanation is something that you could do when you want to increase the heat of the value, but if it's not going to use as fuel, you don't need methanation either. It's just to show that you can add some process to your gasification. And then, of course, you have a syngas with this composition, pure syngas as 82 and CO. So this is basically, and just to show a picture, that's the plastics, the waste, and this is the plastics pulverized, and the plastics pulverized are going in this schema for gasification, and it's processed 1 ton per hour. For each hour, we produce 2,500 cubic meters of pure syngas. And this is syngas not to be used as a fuel, not to be burned, but to be used for chemicals, for the production of chemicals. And here is to show you a picture of the gasify as you can visit it, as we have built, and this is the gasify that you can visit. You can check the quality of the gas and check that everything I'm saying here has based on the reality. So I thank you so much for that, and I hope with this video I have answered some questions which I keep get, but keep asking on the comments, and I may have to do a new video. I will explain as many times as is necessary. I want you all to understand. So thank you so much for that. And let me now finalize this.